Lesson 10.1.3, the chi-square distribution and degrees of freedom. In the previous lesson, you executed a chi-square goodness of fit test where an approximate p-value was provided. In this lesson, you will learn how the p-value is calculated for a chi-square test statistic based on a chi-square distribution. First, degrees of freedom. The p-value calculation for a chi-square goodness of fit test is based on a chi-square distribution. Like the t-distribution that you have seen in previous modules, the shape characteristics of a chi-square distribution are determined by degrees of freedom. For a chi-square goodness of fit test, the degrees of freedom, df, equal the number of categories for the categorical variable of interest minus 1. In other words, if k, capital K, equals the number of categories in the categorical variable of interest, then df is equal to capital K minus 1. Try these. Number 1. In an attempt to identify the ownership status of residences in the United States, a question on the 2010 U.S. Census form asked respondents to choose from 4 possible responses to complete the statement. Is this house, apartment, or mobile home blank? The 4 response choices were 1. Owned by you or someone in this household with a mortgage, include home equity loans. 2. Owned by you or someone in this household free and clear without a mortgage or loan. 3. Rented. 4. Occupied without payment of rent. Part A. If you were to conduct a chi-square goodness of fit test regarding the distribution of the population proportions for these 4 categories of responses, meaning capital K equal 4, how many degrees of freedom would the test have? df is equal to capital K minus 1. So in this case, the degrees of freedom would be capital K minus 1. Capital K is the same thing as 4 categories, so 4 minus 1 is 3. And then continuing on to part B, suppose the first 2 categories, owned by you or someone in this household with a mortgage or loan, and owned by you or someone in this household free and clear, were combined into a single category called owned. If you conducted a chi-square goodness of fit test regarding the distribution of the population proportions for the 3 categories of owned, rented, and occupied without payment of rent, how many degrees of freedom would the test have now? So now the degrees of freedom, again, is capital K minus 1, but now we have 3 categories, so that's 3 minus 1, which is 2. So that gives us an understanding of how to find degrees of freedom for the chi-square distribution. So as stated previously, the shape characteristics of a chi-square distribution are determined by degrees of freedom. The chi-square distribution is a severely skewed to the right distribution for small degrees of freedom. However, for larger degrees of freedom, the distribution's shape becomes less skewed. The 3 graphs below illustrate the chi-square distribution for 2, 6, and 10 degrees of freedom. Each distribution graph has the same scale. So here we can see 3 different graphs, graph 1, 2, and 3. Below graph 1, we see that it says df equals 2. Below graph 2, we see it says df equals 6. And below graph 3, we can see df equals 10. And as you can see, the first graph with df, or degrees of freedom, equal to 2, it is very skewed to the right. You can see that there's a high peak that it starts with, and then a very long right tail. And in fact, there's no left tail at all. So it's definitely skewed to the right. But as the degrees of freedom increases in graph 2 and then graph 3, you can start to see a left tail emerge, and it becomes a little bit less skewed to the right. Continuing on to the next page, unlike a t-distribution, which is symmetric and always centered at 0, a chi-square distribution is not symmetric, and the mean of a chi-square distribution is related to its degrees of freedom. Specifically, the mean of a chi-square distribution is equal to its degrees of freedom. The standard deviation of a chi-square distribution equals the square root of the value 2 times the degrees of freedom. This means that in the chi-square distribution above with 6 degrees of freedom, the mean of the distribution is 6, and the standard deviation is the square root of 2 times 6, which is the square root of 12, which is about 3.464. So, number 2. What are the mean and standard deviation of a chi-square distribution with 8 degrees of freedom? So, in the paragraph at the top of this page, the mean of a chi-square distribution is equal to its degrees of freedom. So we would say that the mean for number 2 is equal to the degrees of freedom, which they told us was 8. And then also in the paragraph above, it says the standard deviation of a chi-square distribution equals the square root of the value 2 times the degrees of freedom. So the standard deviation for number 2 would be the square root of 2 times 8, because 8 is the degrees of freedom for number 2. That's the square root of 16, and that's equal to 4. So for number 2, the mean is 8, and the standard deviation is 4. Number 3, which of the 2 graphs below do you think is for a chi-square distribution with degrees of freedom equal to 8? Hint, look at your answer to question 2. So where we had the mean of 8 and standard deviation of 4. And look at graphs 2 and 3 above on the previous page for the chi-square distributions with df equal to 6 and df equal to 10. Explain your reasoning for which graph we choose. So one thing that we can notice is, remember that with the chi-square distribution with 6 degrees of freedom, the mean was 6 and the standard deviation was 3.464. But now in number 2, with 8 degrees of freedom, the mean has gone up. So maybe that could help us by looking at the graph on the previous page. Notice for degrees of freedom 6, they said that the mean was at 6, which would mean for graph 3, degrees of freedom 10, the mean would have to be 10. So we need to think that we notice that the mean is slightly to the right of the peak of these graphs. If we go down to graphs 4 and 5 that we have to pick from, if we notice that our mean for a chi-square distribution with degrees of freedom 8 has to be 8, which one seems most likely to be the correct answer? It would be graph 5. Because we can see that the mean is just to the right of the peak. In graph 4, this is not the mean of this graph, meaning 8 is definitely not the mean for graph 4. And also, if you think about it, degrees of freedom 8 is between 6 and 10, so we should expect that the graph that we're choosing should be a little bit close to the graphs that we saw for degrees of freedom 6 and 10 on the previous page. All right, that's just a little association with some distributions. Now let's see about finding the p-value. So first, recall that a p-value is the probability of obtaining a test statistic that is at least as extreme as the observed test statistic value if in fact the null hypothesis is true. So this one sentence right here, this is all review. This is now our 4th module of looking at hypothesis tests. This concept of p-value has been the same the entire time. Recall that a chi-square test statistic can never be negative because it involves squares, and larger chi-square values imply a greater discrepancy between observed and expected counts. Thus, the p-value for a chi-square goodness of fit test is the probability of obtaining a chi-square statistic value that is greater than or equal to the chi-square test statistic value obtained from the sample, again under the assumption that the null hypothesis is true. Note, while technology is often used to compute the p-value associated with the chi-square test statistic value for specific degrees of freedom, tables are also available to roughly approximate the p-value. We're going to be using our calculator to find the p-value. So first, try these. Graph 6 below shows the p-value shaded for a chi-square goodness of fit test with 2 degrees of freedom, which is based on 3 categories, and a chi-square statistic value of 3.91. So here we can see 3.91 is the number below the horizontal axis, and then there's a shaded region that is below the curve for the chi-square goodness of fit. And the p-value is pointing at the shaded area, and they're saying that the p-value is 0.142. Graph 7 below shows the p-value, which is shaded, for a chi-square goodness of fit test with 2 degrees of freedom based on 3 categories and a chi-square statistic value of 5.99. So first of all, these 2 graphs, notice they involve the same degrees of freedom, 2 degrees of freedom, but they have different chi-square values. The first graph, graph 6, has chi-square equal to 3.91. Whereas the second graph, graph 7, has a chi-square equal to 5.99. And then notice graph 6 has a p-value of 0.142, and graph 7 has a p-value of 0.05. So then below graph 7, for a chi-square distribution with 2 degrees of freedom, a chi-square value of 5.99 has an associated p-value of 0.05, and a chi-square value of 9.21 has an associated p-value of 0.01. So now they're giving us another chi-square value. If it was 9.21, the associated p-value would be 0.01. So we're going to use all of that in looking at the next question. Number 4, use all of the information above to help you answer the following questions. For a chi-square goodness of fit test, again with 2 degrees of freedom, like we had on the previous page, do you think that a chi-square test statistic of 7.23 would have a p-value that is greater than 5%, between 5% and 1%, or less than 1%? So here in question 4a, they're saying that chi-square is equal to 7.23. So first, let's see how that relates to the chi-squared values that we were given above. We were given 3 chi-square values. The first one in graph 6 was chi-square equal to 3.91. In graph 7, chi-square was 5.99. And then in the sentence at the very bottom of the page, we had a chi-square value of 9.21. So we can notice that in 4a, the chi-square value that we have, 7.23, that's between the last 2 on the previous page. That's between 5.99 and 9.21. So this is between 5.99 and 9.21. So maybe that would help us answer the question. If the chi-square value is between 5.99 and 9.21, what do you think about the p-value? That would be between the associated p-values of those chi-square values. So it would make sense that this would be between 5% or 0.05 and 1%, 0.01. So the p-value should be between 5% and 1%. Again, this is just getting us used to how chi-square values relate to p-values. So as another example, part B. For a chi-square goodness of fit test with 2 degrees of freedom, again, same degrees of freedom, do you think that a chi-square test statistic of 10.73 would have a p-value that is greater than 5%, between 5% and 1%, or less than 1%? Explain your reasoning. So now notice this chi-square value, 10.73, that's greater than the 3 on the previous page. But also let's notice as the chi-square values increase, we had 3.91 and then 5.99 and then 9.21. What happened to the p-values? They started at 0.142, then went down to 0.05, then went down again to 0.01. So as the chi-square values increase, the p-values decrease Again, this is not a new concept. We actually saw this in the previous lesson, 10.1.2. So as chi-square values increase, p-values decrease. So that means it must be smaller or less than 1%. So the p-value for this test statistic, 10.73, p-value will be less than 1%. And then finally, part C. For a chi-square goodness of fit test with 2 degrees of freedom, again, same degrees of freedom, do you think a chi-square test statistic of 4.62 would have a p-value that is greater than 5%, between 5% and 1%, or less than 1%? Explain your reasoning. So here chi-square is equal to 4.62, which is less than 10.73, less than 9.21, less than 7.23, even less than 5.99. So you can think the chi-square value is getting smaller, which means the p-value has to increase, which means it definitely would have to be above the p-value of 0.05 that related to the chi-square of 5.99. So as chi-square decreases, p-value increases, which means it wouldn't be less than 1%, it wouldn't be between 5% and 1%, it would be greater than 5%. So p-value is greater than 5%. Number 5. In lesson 10.1.1, you drew a daily simple random sample of 1,000 cereal pieces from your cereal production process to examine whether there was sufficient evidence against the claim that the distribution of population proportions for the cereal was 20% red, 35% white, and 45% blue. So notice here the claim is the distribution for the cereal was 20% red, 35% white, and 45% blue. So saying that the proportions were exactly these numbers. So this is the null hypothesis, as we saw before. The null hypothesis in this case is the same thing as the claim. Recall that the rule for determining whether to reject the null hypothesis in a chi-square goodness of fit test is the same as for the other hypothesis tests. Reject the null hypothesis if the p-value is less than or equal to alpha, where alpha is the significance level. Also recall from the previous lesson that a complete chi-square goodness of fit test requires the following: find the null and alternative hypotheses, state the conditions, and examine if they are met. Remember that was we needed a random sample and that we also needed our counts to be greater than 5. Number 3, compute the chi-square test statistic, as we saw before. Compute or approximate the p-value, which we're going to learn how to do on the next page. And then finally, decide and conclude using that rule, reject the null hypothesis if the p-value is less than alpha. And then stating our final conclusion in context. So we're going to do all of that on the next page. So we look at part A, which says the sample data for day 1 were as follows. So this goes back to lesson 10.1.1. So go back and take a look at that if you need a reminder. Using the day 1 sample data and a 1% significance level, perform a complete chi-square goodness of fit test, examining the claim that the distribution of population proportions for your cereal is 20% red, 35% white, and 45% blue. So as we learned in the previous lesson, our null hypothesis involves the symbol pi. Pi for population proportion. Here, we're going to say pi with a subscript red, pi with a subscript white, and pi with a subscript blue. We could use pi sub 1, 2, and 3 if it makes sense that red is 1, white is 2, and blue is 3. But it doesn't matter, just some way to help us stay organized. And again, what comes from our claim, which is the same thing as our null hypothesis, is that pi sub red should be 20%, but we want to write that as a decimal, 0.20. Pi sub white should be 0.35, and then pi sub blue should be 0.45. And then our alternative hypothesis, again like we saw in the previous lesson, we would say the distribution is not as stated in the null hypothesis. Remember, there was 3 options for that. I'll usually be gravitating towards that one. So step 2, we need to take a look at the conditions. So first of all, in what was given in number 5, we did have a random sample of 1,000 serial pieces. So we have a random sample. And then we need the expected counts we need them to be greater than 5 for each category. So remember what we did for this, we took our sample size and we would multiply it by the proportions that come from the null hypothesis. So we needed to look at n times pi sub red, and then n times pi sub white, and then n times pi sub blue. So this means we take our sample size, 1,000, and then multiply it by 0.20, the proportion for red, and that gives us 200. And then we also take 1,000, our sample size, multiply it by the proportion for white, which is 0.35. That gives us 350. And then for blue, 1,000 times 0.45, and that gives us 450. So these are all greater than 5, so we've met our conditions. Then step 3, we need our chi-square value. So go back to lesson 10.1.1, and you'll see that we already did this, and this was just before number 7, and I believe this is on page 286 in your workbook. You'll see that we got chi-square equal to 1.68. All right, so we've got our chi-square value. We've already done the work for that. So now our p-value, step 4. This is the new thing that you learn in this lesson. So just like we found p-value before, on your TI 83 or 84, second, and then vars. And when you select that, remember we did normal CDF, then we did TCDF. Go down 2 more until you find chi-square CDF. So then our p-value, that would be chi-square CDF, and you have to put in 3 numbers. The chi-square left number, the chi-square right number, and then your degrees of freedom. What's easy is that chi-square tests are similar to things that we saw before that just had a right tail. All of these numbers are positive, so we're only ever going to be using our chi-square value as the chi-square left, and then 1e99 as the chi-square value right. So we would have chi-square CDF, our chi-square value, which was 1.68, comma 1e99, and then our degrees of freedom is 2, and you will get approximately 0.432. And so that's how you find a chi-square value PDF. Okay, so then finally, step 5. How does our p-value relate to alpha? Well, if our p-value is 0.432, that is definitely greater than alpha, which is 1%, or 0.01. So, this tells us that we fail to reject the null hypothesis. So then we just need to write a conclusion. So since we fail to reject the null hypothesis, it means that we do not have evidence to reject the claim that the distribution of population proportions for your cereal is 20% red, 35% white, and 45% blue. Also, if you think about how this was relating to a process that they had in production, we would go back and also say it doesn't seem like there is anything wrong with the production process. So, summarizing all of that, the data does not imply that something is wrong with the production process. You might need to go back and read over what we saw in 10.1.1 to be reminded that that was the context for looking at these cereal samples. So then one more example, part B. Now we're looking at the sample data for day 4. Using the sample day 4 data and of 1% significance level, perform a complete chi-square goodness of fit test examining the claim that the distribution of population proportions for your cereal is 20% red, 35% white, and 45% blue. So what would we say for step 1 for our null and alternative hypotheses? This would be exactly the same as what we saw in part A. So we don't need to write that again. Number 2, do we still have a random sample? Yep. And are we still going to have the same expected counts? Yes. So again, this is also the same as part A. So then step 3, what is our chi-square value? Again, go back to lesson 10.1.1, number 7C in the middle of the lesson. You'll see that we've already calculated this. Chi-square equals to 9.752. So now maybe before we even find the p-value, do you expect that it's going to be smaller than what we got before? The chi-square value has gone up from part A to part B, so that means the p-value should go down. So let's see. We know that our p-value would be equal to, using second, vars, and chi-square CDF, it would be our lower chi-square value, the one that's on the left, 9.752, and then 1E99, and then degrees of freedom, which is 2, and when you plug that into your calculator, you should get 0.008. Notice the p-value has gone down. So then we are going to get a different conclusion than we saw in part A. P-value of 0.008, that's definitely less than alpha, which is equal to 0.01. This tells us that we reject the null hypothesis. So that means that our data does not support the claim. Since the claim and the null hypothesis were the same, the data does not support the claim. And then we could use the wording of the claim, if we want, from the description in number 5. The data does not support the claim that the distribution of population proportions for the cereal was 20% red, 35% white, and 45% blue. I'll let you finish that sentence on your own. You can find that wording in number 5. And to finish this lesson, the secret word is blue.